This week, we are joined by Dr. Michael Hope, who earned his PhD in the group of Claire Gray before accepting his current postdoc position with Lyndon Emsley at the EPFL. Additionally, we are adding this week an extra expert member to the panel to help field questions on the topic at hand with Dr. Carina Merker. Dr. Merker earned her PhD in the group of Gael de Pau before accepting her current postdoc position in the group of Claire Gray. Today's topic will be on NMR in metals, night shifts, Overhauser DNP, and some applications. So following last week's model, we'll be taking a short break for questions during the presentation, so please feel free to make them known via the Q&A function. All right, take it away, Michael.
Okay, thank you very much. Can you hear me all right? I'm going to assume yes. Let me know if you can't hear me. Okay, so this Zoom tutorial is going to be in two halves, and it's in general trying to pass on some of the things I spent a long time during my PhD trying to get my head around, and hopefully that will be useful to some of you. The first half is going to be these sort of NMR signatures we get in metals, so night shifts in particular, and after that section it will be the first break for questions. In the second half, slightly different, going to be talking about how we can use dynamic nuclear polarization to boost signal in metals. Where I say some applications, it's not being quite accurate. What I really mean is shameless self-promotion, in that I'm just going to be talking about a couple of my projects that relate to this area. Okay. So just to start off, a brief recap on paramagnetism in general. So as we know, spins have a magnetic moment which couples to applied fields, and in an applied field they align so that they augment the applied field. This is what we mean by paramagnetism. In the case of localized spins, this paramagnetism is dictated by the population difference between the nuclear spin levels, the up and down spin levels in the case of spins half. And this is known as Curie paramagnetism. And so the size of the magnetic response is dictated by the population, which is given by Boltzmann statistics. So this depends on the energy separation. And so we know that the electron has a larger gyromagnetic ratio, so it has a larger energy separation, a larger paramagnetic response than nuclear spins, which have smaller energy. But the other key factor is temperature. And these Curie paramagnetic response has a very strong temperature dependence. And in particular, you have to go down to very low temperatures to get large paramagnetic responses. The final thing I want to say on the slide is to say that electron spins can couple to nuclear spins, and in the NMR spectrum, we see that as a shift, and this is known as a paramagnetic shift. And this also has a strong temperature dependence due to Curie paramagnetism. All right, so that's the case for localized spins. What about in a metal? So in a metal, we have delocalized electrons that form a continuous band, and this band is partially filled. So rather than discrete spin states, we now have a band of spin states. I'm showing that here with an up spin band and a down spin band. And we put in our electrons, and the highest energy they reach is known as the Fermi level. Okay, what happens when we put this in an applied field? So in an applied field, the bands then move in opposite directions. One's raised in energy, one's lowered in energy, but we still have this common Fermi level. You can think about this just as like water flowing down to a lower gravitational potential energy. Electrons are just moving down to lower energy states here. So we have this common Fermi level. That means that we have now a net unbalance in spins. We've got more of these spins than we do of these spins, and so that results in a magnetic moment which augments the applied field. So again, this is a paramagnetic effect, but this is known as Pauli paramagnetism. And in contrast to Curie paramagnetism, this is a temperature independent effect, at least in most cases, and to at least a couple of degrees of order. And the reason for this is temperature can cause sort of smearing out of this Fermi level, so we excite some of these electrons into these states, but this happens exactly the same way in the two spin bands, and so we still end up with the same difference in population, and so we still end up with the same magnetic moment, and so the magnetic moment here is temperature independent, and that's a characteristic of Pauli paramagnetism. Okay, what does this do to our NMR? So in NMR, what we see is a night shift. And a night shift is the hyperfine coupling of a nuclear spin to the net delocalized unpaired electron Pauli paramagnetic spin density. Or, in other words, the coupling to what I just described on the previous slide. This was first reported by Walter Knight in 1949. And what it requires is that there's some coefficient of the unpaired electron density at the nucleus. The simplest way this can happen is if we have s orbitals. So s orbitals are the only orbitals which have a coefficient at the nucleus. And so if we have valence s orbitals that are partially filled at the Fermi level, then this gives us a Fermi contact, and this gives us a positive shift, which is known as a direct contact night shift. And this is the case in alkali metals, for instance. So showing that here, the case of lithium metal, the 7 lithium spectrum, and you may be familiar that in diamagnetic lithium compounds, everything comes within a few ppm of 0, which is quite frustrating if you're trying to assign lithium spectra, but lithium metal comes out here at 270 ppm. And that's because we've got these delocalized unpaired electrons due to this Pauli paramagnetism. In s orbitals, they have a direct Fermi contact shift on our 7 lithium nuclear spins. Okay, so that's what most people will think about when they think of a night shift. But what if we don't have any s orbitals at the Fermi level? Turns out we can still get an effect, and we get an effect by polarizing core s orbitals. And so this is known as core polarization or indirect contact night shift. And this actually results in a negative night shift. We'll see why that is. So what I'm showing here is a core filled s orbital, and there's an up spin orbital and a down spin orbital, but in the absence of any other effects, these have the same spatial dependence, they're coincident. Okay, now let's imagine we have some unpaired electron density in our valence orbital. I'm showing this for a d orbital here. Now our core up s spin orbital is going to expand into that space. That's because it's energetically favorable to do so via the exchange interaction, whereas our down spin orbital contracts for the opposite reason. So we still have the same amount of electron spin. This is a closed shell, completely filled s orbital. We've just changed its distribution. And if we plot that, so in red is our up spin band that expands slightly, blue is our down spin band which contracts slightly, and we can see that the net effect is we have an excess of down spin at our nucleus, and that's what gives us that negative night shift. So one example of this is in VO2. This is something I looked at during my PhD. And so VO2, vanadium dioxide, is interesting because at room temperature, it's an insulator. And so in the vanadium, 51 vanadium spectrum, you end up with a shift of 2000 ppm. But then if you heat it above 67 degrees centigrade, it transitions into a metal. And this results in a 7,000 ppm shift in the 51 vanadium spectrum. This wasn't new at the time either. This has been known for many years. But this is a negative night shift we're observing here because there are no s orbitals at the Fermi level. The valence orbitals here are vanadium d orbitals, and so they cause core polarization of the vanadium core s orbitals, and this results in a negative night shift. So you might have been asking, why did the insulating phase come at 2000 ppm and not 0? This is to do with Van Vleck paramagnetism, which is sometimes called an orbital night shift. I don't want to spend a lot of time on this, partly because I don't really think it's a night shift, but this is the same thing as the paramagnetic contribution to diamagnetic shifts, for those who are familiar with that. And it comes from mixing filled and empty states. You can see this coming about via second order perturbation theory. And this always ends up with a positive shift. And put simply, you sort of weight the weighted by the energy difference of your filled and empty states, and terms involving their symmetry results in a shift. And so if you have filled and empty states that are close in energy, you get a large shift. And so that's obviously can be the case in metals, but can also be the case in insulators with small band gaps, and it happens to be the case in the insulating phase of VO2. And so that's where the positive 2000 ppm shift came from in that phase. I'd be happy to talk more about this, but it's not really what I want to get into right now. What I do want to tell you about is this, because this took really quite a long time to get to work. It turns out that you can also hydrogenate VO2 at room temperature. Sorry, you can also metallize VO2 at room temperature by hydrogenation. And you can do this either electrochemically or catalytically. And the way you can tell that you've turned it into a metal is you get this peak here appearing in the proton spectrum. So this is around 100 ppm, which is well outside the diamagnetic range for protons. And this is a positive direct night shift, because the valence orbitals on the protons are s orbitals, the 1s orbital. And by doing variable temperature experiments, I could show that this was temperature independent, and therefore this was a night shift and not a paramagnetic shift. Okay, with that, I'd like to summarize the first half of this tutorial. So metals have partially filled, delocalized bands of electrons, and in an applied field, we end up with a net unpaired electron spin density, which augments the applied field, and this is known as Pauli paramagnetism. This is a temperature-independent effect. This can then couple to nuclear spins, and in an NMR spectrum, we see this as a night shift. If we have s orbitals, valence s orbitals at the Fermi level, we get a positive shift, it's a direct night shift. But if we don't have s orbitals, we can still get an effect, and this is known as an indirect or core polarization night shift, and that is negative. Okay, stop there. Are there any questions at this point?
We have one from David Bryce. I don't know, Michael, if you can take a look at it, otherwise I can read it out to you.
Yeah, so I can see that. So the question is, does Van Vleck paramagnetism compete with indirect night shifts in metals to determine the overall shift? The Van Vleck term is a second order term and tends to be much smaller than sort of night shift terms. Indirect contact night shift or direct contact night shifts. But it does also depend, so you can see in the second order term, the denominator had the energy difference. And so in a metal, your filled and empty states are right next to each other. And so due to symmetry, they're not right next to each other, but that term can get quite small. And so you can get quite large Van Vleck shifts. I think this is the case in some of the first row transition metals. These as in pure metals. This ends up being more significant in some cases. There's a very good review on the relative contributions. They can be comparable, but typically the Van Vleck contribution is smaller. Just
another question from Dylan here.
Okay, so yeah, I mentioned d orbitals as an example for core polarization. Dylan was asking whether you can also get it for p orbitals, and the answer is you can. You can get it for any non-s orbital. What dictates the magnitude is how close that valence orbital gets to the core s orbitals. So how much density there is sort of nearby. And something I didn't get into is for 2p orbitals, the indirect night shift is actually positive because it actually polarizes your core orbital the other direction. So you have to be a little careful with elements that are early on in the periodic table because you can get unexpected results there. But yes, in general, they apply to all non-s orbitals.
Let's see, I think we could probably get at least a few more questions in before we move along. We have one from an anonymous attendee. How anisotropic is the night shift?
So the anisotropy of the night shift depends on two factors: the anisotropy of the susceptibility, the magnetic susceptibility, and then the anisotropy of the coupling of that susceptibility with the nuclear spin. Fermi contact is, which is the main interaction which actually gives you a shift. The Fermi contact interaction is isotropic. So in order to get an anisotropic night shift in that case, you would require an anisotropic susceptibility, which can be the case, especially if you have more complicated band structures. The other contribution you can have is dipolar coupling between your nuclear spin and your electron rather than Fermi contact. So that results in anisotropy, but it tends to actually be pretty small. The dipolar coupling with the delocalized electrons is comparably small, and so you end up with an anisotropy that is not as big as, for example, in some paramagnetic systems, localized paramagnetic systems with paramagnetic shifts that can be very anisotropic.
I think we can maybe get one last question in, and maybe have to save the rest for last, or at the end, I should say. So we'll just go in order here. What effect did metallization have on the vanadium spectrum? From Brendan Hawkins.
So the vanadium spectrum is what I'm showing here, and this is the 7,000 ppm shift on metallization. Oh, do you mean in the case of the hydrogenation? Because that would be a better question. So it depends on the degree of hydrogenation, and if you're interested, I direct you to this the paper at the bottom. It turns out that actually for that spectrum I showed you, this one, this was actually for a very low amount of hydrogenation. It's on the order of 3%. And this was actually localized metallizations. It didn't result in metallization of the whole sample. And so the vanadium spectrum actually looked pretty similar. If you hydrogenate further, then yes, you end up with a vanadium spectrum which looks more like this one for the fully metallized sample, except way broader, because you also have then a distribution of metallizations. You have different local environments due to the protons. So it's negative, but it's less well defined.
All right, and so with that, let's go ahead and continue, and we'll address the rest of the questions once we get to the end.
Okay, so thanks. I wanted to shift gears a little bit now and talk about Overhauser DNP. And so for those not familiar with dynamic nuclear polarization, this is a technique to boost the signal in NMR experiments by exploiting the higher polarization of electron spins, this higher polarization, which I very briefly mentioned on the first slide. And so many of you are aware that this has been a very successful technique that's applied to solids. But this was first described by Overhauser and then experimentally verified by Carver and Slipter in 1953. And in both cases, they were talking about nuclear spins in metals, whereas nowadays we're typically looking at localized radical systems. So how does this work? Why do we get a boost of sensitivity in our NMR spectrum in the case of metals? So here is our metal again. We've got our up and down spin bands. We put it in an applied field. We shift our spin bands, and then we get this common Fermi level. So we have an applied applied moment, induced moment. But in an Overhauser DNP experiment, we then irradiate with microwaves at the electron resonance transition, and this partially saturates the transition, and so we end up, at least partially, with equilibrated populations of our up and down spins. And we can see that this is a higher energy arrangement than this one. We've raised these spins in energy, and they want to relax back to equilibrium. They can do this via cross-relaxing with nuclear spins, and that's what generates our nuclear hyperpolarization. So we irradiate with microwaves, equilibrate the population, and then as it relaxes back, it hyperpolarizes our nuclei. So why is that? So I'm going to show this now to the case of a 4-level system. This is a bit of a simplification because in a metal these are all bands, but it suffices to explain the effect. So what I'm showing here, on the left, our nuclear spins are up, and on the on the right, our nuclear spins are down, and then at the bottom, our electron spins are down, at the top, our electron spins are up. So we start off at thermal equilibrium with an excess population of these lower energy states, and then we irradiate with microwaves, that's the green wiggly lines, and we populate these upper levels. Now this is a higher energy arrangement. It wants to relax back to equilibrium, and it can do this via single quantum relaxation. That's the red lines. And if that happens, nothing's really changed. What can also happen is we can get cross-relaxation, zero quantum cross-relaxation. That's this blue arrow. And that's when we simultaneously flip an electron spin and a nuclear spin in a sort of a flip-flop. And then you can see if we repeatedly repeatedly irradiate with microwaves, or continuously irradiate with microwaves, we repeatedly populate these levels, and some of the time they fall down this way by a zero quantum relaxation, we're going to end up with an excess of population on this side. So we have more nuclear spins up than we would have at equilibrium, and so that's the hyperpolarization, the boost in our NMR signal. Those of you who are maybe more familiar with DNP, or indeed the Overhauser effect, might be asking why I haven't shown double quantum relaxation, which is the one that goes the other way. This is because, as I sort of mentioned earlier, the hyperfine coupling is dominated by Fermi contact, and this is an isotropic interaction, and so it can't drive zero. It can only drive zero quantum relaxation. To get double quantum relaxation, you need an orientationally dependent interaction like the dipolar coupling, and this is much weaker. So the zero quantum cross relaxation dominates. The other thing we need in order to get this cross relaxation is spectral density at this transition frequency, in metals, that comes from rapidly moving electrons at high kinetic energy, and so that's where that spectral density comes from. This is in contrast to the Overhauser effect in insulating solids, where I believe it's still an open question where that spectral density comes from. But in metals, it's very well understood that it comes from rapid motion of the electrons. Okay, this is now, if we have a constant frequency of microwave irradiation and we sweep the field, we get no real effect until we hit the electron resonant frequency. So when our microwaves match the resonant frequency of our electrons, that's when we get saturation of the transition. We start to equilibrate these populations, and then they can cross-relax and hyperpolarize nuclei, and we measure that as an enhancement. And this is a pretty sharply peaked effect. Again, for those unfamiliar with DNP, this differs from the solid effect and the cross effect, where you see multiple features. In a characteristic of the Overhauser effect is that we see just a single feature at the electron resonant frequency. Okay, what does this look like? So this is the now famous spectrum of carbon restrictor. At the top, this is the lithium spectrum of lithium metal without microwaves. And then at the bottom, this is when they turn the microwaves on, and we can see we get a big boost in the NMR signal. But these are very different experiments to what we now consider as a sort of contemporary DNP. They're very low fields. This is 3 millitesla. So your lithium is at 50 kilohertz, electrons are 84 megahertz. They're under static conditions. And importantly, they're also performed at room temperature. So typically DNP is performed at 100 Kelvin or even lower. That's to slow down the electron relaxation so we can harness its polarization. In the case of lithium metal, the relaxation is temperature independent. So there's actually no benefit to cooling down. And this works just as well at room temperature. Okay, so this is what we could do in 1953. And you can see in 2019, we've got much better at making figures. Okay, this also, we've made some other progress. I mean, this is now at 14 Tesla, so that puts our electrons at 395 gigahertz. And this is only possible now with the gyrotron technology, which has been developed. You see we have much higher resolution. These are also performed under magic angle spinning conditions, 12.5 kilohertz. But again, this is at room temperature. And we can see in red, this is with microwave irradiation, and we get a significant enhancement compared to the microwave off spectrum blue. The other interesting feature here is with microwave irradiation, we've enhanced the spectrum, but we've also spread it out to lower frequencies. And this is actually a result of the microwave irradiation, because the whole point of the microwave irradiation is we want to saturate that transition, we want to equilibrate the population. But the shift here, this is the night shift, this is at 270 ppm. This night shift is caused by the unpaired electron density, it's caused by the paramagnetic moment. So when we irradiate with microwaves and we reduce that moment, we reduce the population difference, we also reduce the shift. And really, this shows us that we don't have very good saturation at all. If this was perfectly saturated, it'd be down at 0 ppm. And so we're actually only getting very small saturation. And that's because it's we don't have a large enough B1 field of our microwaves at this high frequency. And that's probably the main reason why we don't have higher shifts. We just, higher enhancements. We just need more power. Okay, so this is all well and good, so reviving 70-year-old science, but we wanted to do something different with it. And we were looking at, this is a battery group from Cambridge, so we were looking at lithium metal batteries, and these could have higher energy densities than traditional graphite anodes, but the trouble is that they form dendrites. These are sort of microstructures that can grow across and then short circuit your cell and set it on fire, which is not ideal. It turns out that the nucleation of these dendrites depends on lithium transport across the solid electrolyte interface. This thing here. This is a mixed inorganic, organic, heterogeneous film that passivates the surface of any exposed lithium metal, so including on the dendrites. In general, this is quite a challenging species to study because it's heterogeneous, it's nanoscale, and ideally you want to form it in situ. And in particular, we want to study this interface here because that's where the nucleation happens, right at the interface between the metal and the SEI. And so you can see what we're going to do. We're going to irradiate with microwaves, hyperpolarize our lithium, and then we're going to transfer that into the SEI. This is very different to previous DNP experiments that have been performed on the SEI, where external biradicals were added. And in these experiments, you have surface selectivity to the outside of the SEI, but you can't selectively observe this interface, and that's really what we're doing differently here. So just to quickly show you some of these results, in red is with microwaves, blue without microwaves. This is the diamagnetic lithium spectrum now, so the spectrum around 0. And you can see that there's an enhancement on irradiation of microwaves of the metal. But importantly, this isn't uniform. So this sharp peak here is the electrolyte. It's residual salt in the electrolyte that has been washed away. That's not in the SEI. It's not in contact with the metal, and so it's not enhanced. Whereas these other species are in the SEI, and they are enhanced. We can also look at their relative enhancements, and that tells us something about the spatial distribution relative to the metal. We also looked at protons. So in the proton NMR, this is a direct spectrum, just protons with and without microwaves. We get enhancements. They're pretty minor, around a factor of 2. But again, the impurities aren't enhanced, and so this is giving selectivity. And if we take a different spectrum, we have a spectrum that's just of that, the SEI near that interface. You can also do cross-polarization experiments from lithium to proton, and this gives you larger enhancement, and it's sensitive to polymeric species that coordinate lithium ions that are very broad and hard to see in the direct spectrum. Finally, we looked at fluorine. So in the direct fluorine spectrum, you see the PF6 anion that comes from the electrolyte. That's not in the SEI. The SEI is impermeable to PF6, and so it's not enhanced. We see nothing in the different spectrum. However, if we do lithium to fluorine cross-polarization, we can now reveal lithium fluoride, pretty low concentrations of lithium fluoride. But importantly, we get a very large enhancement compared to the enhancement of other lithium species. And that tells us that this lithium fluoride is right at the surface of the lithium metal. And that's something that had previously been proposed, but it's quite difficult to prove. Okay, with that, I just sum up this section. So irradiation of the electron resonance transition in metals causes nuclear hyperpolarization. And this occurs by cross-relaxation of nuclei and is known as Overhauser DNP, as first demonstrated in 1953. For the case of lithium metal, you can do this at room temperature because the relaxation is temperature independent, and that works just as well as 100 Kelvin. And what we've done differently, we've demonstrated that this also works at high field, which we need for resolution. We then showed that you can harness this hyperpolarization and transfer it to an adjacent phase, and this allows you to study buried metal-solid interfaces. And in particular, because we control where we introduce the polarization in the metal, we can extract spatial distributions from the relative enhancements of different species. So I'd like to thank the various co-authors on the 2 projects I described, as well as Cambridge and Claire, where these projects were performed. I'd also like to thank EPFL, where I'm now working as a postdoc with Lyndon Emsley. I'd be happy to take any more questions. Thank you.
All right, and thank you, Michael. It was a very nice talk. At this time, we'll bring in Carina to help field some of these questions. We've collected quite a list. So maybe starting from the top a little bit more from that first section, can you comment on the relaxation effects when nuclei undergo a night shift?
Yeah, I can. I'm not sure it's going to let me do this. I did have a slide, and then I decided to remove it for the sake of time. It's a relation known as the Carina relation. Probably going to have to go out and go back in again. I've got so many things up on my screen that I can't actually find the button. There we go. Without going into too much detail here, the Kaminker relation tells us what relaxation we should expect in metals, and it turns out that this is proportional to the night shift squared and is linear with temperature. So this is is a really good way of testing whether you actually have a night shift or not, is look for a linear temperature dependence of the relaxation. And often in metals, this is the mechanism that dominates. It's to do with the metallic electrons fluctuating, sort of spin up, spin down very, very rapidly, and that's what induces this nuclear relaxation, if that answers your questions.
And kind of also back, maybe go to this next one as a pretty foundational one, but a quick re-explainer on the nature of the spin bands and exactly what the spin band means.
Well, to start off with, a band is just a continuum of possible levels for your electron. So in molecules, you have discrete energy levels, but in a solid, or at least in an infinite solid, you have a continuum of possible energy levels. And then spin bands are just the band equivalent. So if you have localized electrons, you know that you can have an up spin level and a down spin level, or nuclear spins, you can have an up spin or a down spin level. Spin bands are just the case in solids, where you have bands, but you have an up spin band or a down spin band. Normally, we think about them together. We don't separate them because we're not interested in magnetic response. But it's just sort of another way of thinking about band structures, because you can't have two particles of the same spin occupying the same energy level, which is why we can think about them being separate.
And then kind of also back in this first half, what determines the extent of direct and indirect night shifts?
So that's really dictated by whether you have s orbitals. So the first question is whether you have direct or indirect. To have direct, you need s orbitals at the Fermi level that are partially filled, and if you have that, the direct will almost always dominate. It's just a larger effect. The actual magnitude is of a direct night shift, for instance, is simply proportional to the density of states, the S density of states at the Fermi level. And so that's dictated by the dispersion in your band structure. But this is something you can measure or you can predict with calculations. Indirect night shifts are more complicated. They also depend on the density of states at the Fermi level of whatever your valence orbital is, because that tells you how much Pauli paramagnetism you have in the first place. Or put another way, it just depends on the Pauli paramagnetic susceptibility. But then it depends on your core orbital electronic structure, and actually this has been tabulated, because the core of elements are pretty well understood, and so you can just look up in a table sort of the conversion factor of, okay, what orbital do I have in the valence? How much effect would I expect for each of my different core s orbitals?
All right, and with that, let's move into the second half. We have a good amount of questions. On slide number 14, I believe this is where this is addressed. How is the cross relaxation measured?
So, Katerina, do you want to maybe field this one?
Well, I don't have a good answer for this, except we don't measure directly the cross relaxation here. Or am I missing something in question?
No,
So, I mean, in the end, our enhancement would be a measure of how well the cross-relaxation works, but we're not measuring it directly. Do you agree, Mike?
Yeah. Yeah.
All right. And then, do you expect the DNP of a metal to always have a positive enhancement? Is another question.
So that just depends on the gyromagnetic ratio of your nucleus. So assuming the zero quantum relaxation will dominate, I don't want to tie myself down to maybe if you have transition metals, I'm not sure necessarily whether Fermi contact will dominate. I still think it will, but I'm less sure. But assuming that zero quantum cross-relaxation dominates, then it's solely dependent on the sign of the gyromagnetic ratio of the nucleus. And so for lithium, that's positive, and we get positive enhancement. If you had a negative gyromagnetic ratio, you'd have a negative enhancement.
All right. And then next on the list, when you mentioned that your microwave power, you don't have enough to fully reduce that night shift, if you extrapolate out, how much power do you think you would need to reduce it fully to zero?
Yeah, want to guess at that one, Katerina?
I don't think anything we can get to at these high fields, not with this setup. I mean, if we just see by how much we're changing the night shift right now, that's maybe less than 50 ppm. So we would need a lot more microwave power to be able to do that. It's easier at lower fields, of course. There are old papers showing that to reduce the night shift by at least 50%, but that's much lower field.
Right, and our next question from Quentin Chapuis. How is the spectral density of the electrons in the metal influenced by temperature? Does it end up having an effect on the DNP enhancement?
Have you thought about that, Katerina, or do you want me to speculate?
Well, I can comment on observations that the DNP enhancement in lithium metal, at least, changes a little bit with temperature, but not much. We tend to see slightly higher enhancement but at 100 Kelvin, but the gain we get in resolution at room temperature outweighs that normally.
In fact, thinking about it, so the spectral density actually shouldn't change that much as a function of temperature, because the electrons that you're sort of looking at are the ones with almost the Fermi energy of kinetic energy, which is actually a very high kinetic energy. As I mentioned, as you change the temperature, you sort of smear out the Fermi level a bit, but you still stay quite close to the Fermi level, and so your electrons still have pretty similar kinetic energies. So it might change a bit, and maybe that's something that maybe that's one of the reasons for us seeing slightly different enhancements at different temperatures. But actually, I don't think that the spectral density should change too much.
Right, and next one on our list, and it seems that we are gaining more, which is excellent as time goes on. Why is the T1E of the lithium metal temperature independent?
This comes from the mechanism, I guess, obviously. So electron relaxation in lithium seems to be dominated by scattering with impurities. And so you can make the electron relaxation longer and longer by just getting more and more pure lithium. And there's some interesting old ESR papers where they show that. Other metals with other mechanisms, so in particular, when spin-orbit coupling is driving a relaxation, that's temperature dependent. Whereas in lithium, perhaps because it's so early in the periodic table, that the spin-orbit coupling doesn't play a role, and it seems to be dominated by scattering with impurities.
This next one might be a quick answer, but how does the Overhauser DNP scale with applied microwave power? Is it linear or is it non-linear?
Is in the amount of enhancement, or?
Presumably, yeah, the the DNP enhancement. Although
it's certainly, I would expect to scale linearly with the amount of saturation you get. I'm not sure that the amount of saturation you get scales linearly with power. Do you know, Katerina?
No, can't tell very well from our measurements because they're a little challenging sometimes. When you change the power, you change your peak position slightly. And you have to be quite careful doing these measurements. So we don't have a good answer for that now, I think.
Okay. All right, and Scott Carnahan has a question here with why does the lithium-7 spectra show hyperpolarization around 0 ppm and not shifted to plus 300 ppm? I know you need peak overlap to cause spin diffusion. How do you explain how the metal was able to polarize the diamagnetic phases?
So this is maybe still an open question. So there are two possible ways that you can imagine hyperpolarizing a diamagnetic lithium. One is you hyperpolarize the lithium in the lithium metal, so the 7 lithium in the lithium metal, and then you get spin diffusion. Because we do have some anisotropy of our interactions and we're under magic angle spinning conditions, you can still get spin diffusion, I think, for that reason. The other possibility is that you have diamagnetic lithium that's sufficiently close to the metal surface to directly interact with the electrons and undergo DNP directly. And so I've said spin diffusion in my slide, and that's maybe not a definitive answer. I think Katerina has maybe been thinking about this a lot more than me. Do we have an answer now?
We've done measurements into this, but they're not ready yet, I would say.
Okay, so I think it should be possible to have spin diffusion, at least feasible. It's not the only possibility, and yeah, that's obviously something we want to answer ourselves.
Alrighty, we have following up an anonymous question as to, have you looked into the lithium 7 to 13C polarization transfers?
You know, I was just about to, and then I crashed the triple resonance probe. So I don't know whether we've had any further success or have we tried that, Katerina. It's obviously something we want to try.
All right. So we'll look forward to more news on that. Next question saying, awesome work looking at the SEI arrangement. Maybe I missed this, but do you also see a lithium 2 oxide near the lithium metal surface?
Katerina, do you have a better internal shift reference for lithium species than I do?
No.
The lithium fluoride sort of is the easiest to distinguish because it's the only thing we should see in the lithium to fluorine CP. The other species sort of overlap a lot, and so we do have a more detailed discussion in the paper about what exactly we can potentially assign shifts to. It was only really the lithium fluoride that was very definitively much higher enhancement than other species, and therefore was definitely at the surface. Everything else was a little bit less clear-cut.
Mm-hmm. All right, this next one is a little bit more on the nuts and bolts, but could you tell us a bit about how you prepare or pack a lithium-related sample, or perhaps both pure metal, more heterogeneous ones, and what kind of precautions you go for when related to oxygen and moisture sensitivity?
This is definitely you, Katerina.
Yeah, I can take that. So they're all packed in a glove box with an argon atmosphere. So the lithium metal shouldn't be reacting with anything. And it's not just a piece of lithium metal that you take out of a bottle or anything, because we're also worried about skin depth effects here. So microwaves and also radio frequency can't penetrate metals very far. And so what we've been looking at were these microstructures, not only, well, mainly because the SEI is interesting, but also they have the effect that they're very thin, 100 micron diameter, if I remember correctly, so that we're less bothered by skin effects and we have more surface that we can actually work with. And the way we produce these samples is in an actual battery. So we make coin cells where we have lithium chips on either side, and we then charge these cells, and within this process, we form these microstructures on the top of one of these lithium chips, and then we open it up in a glove box and basically scrape off the first layer on the surface of these lithium chips. You kind of see that. And then, yeah, we dilute this with a bit of KBR, pack it in a sapphire rotor generally, and close it off. And then it's airtight enough that we can work with that for a couple days, probably without seeing too much reaction of the lithium metal with air or anything else.
Okay, so then the next question on our list is, could you identify all the heterostructures, the interface of the lithium and SEI?
So we can certainly identify, I would say, all the different chemical species. The actual structure is not really something that we're sensitive to. We're sensitive to, the distance from the lithium metal, but knowing whether that's porous or dense or structured in any way is not something I think that we're really sensitive to. You have to wait for lithium metal MRI, which I don't know if that is possible. It's just that's something off the top of my head. So I don't think that we're sensitive to that detail.
Right. So our next on the list is there can be other complications in the Fermi contact interaction with Curie, anti-Curie, and non-Curie, temperature dependent, and no Curie behavior is independent. So is temperature independent. So how will this be different with night shifts? It's a bit of a long question. Hopefully, all got in there.
So often you have some sort of physical intuition to your sample, and you know whether metallization is whether you expect it to be a metal or not. I mean, that's the first information that you should take in. I have to say that I'm sort of not familiar with no Curie or anti-Curie behavior. Just to give a flip side, that sometimes the night shift is temperature dependent. If you don't have equal Fermi surface for your two spin bands, and so yes, there are definitely complications. You should definitely take everything I've said with a pinch of salt. This is all sort of the canonical description of night shifts, and in more complicated systems, of course, it is more complicated.
Mm-hmm. All right. Next one up is where exactly the temperature dependence plays a significant role in the polyparamagnetism.
So polyparamagnetism should be temperature independent, at least in sort of standard cases. You can get temperature effects due to very high temperatures or very narrow bands. So when your temperature becomes comparable to the width of your band in energy units, then it's temperature dependent. Also, if you have correlation effects, you can also get some temperature dependence.
Right. The next one is, can you comment on DNP from other metals such as copper 2+ or?
This is very much an area we want to move into. We want to see what systems this works in. It's not something we've currently looked at. The key factors are the electron relaxation. I say that's the most key factor. You need it to be sufficiently long that you have any chance of saturating your metal. And so we're looking into other systems where that's the case, but I couldn't comment directly for copper.
I'm going to skip ahead. Jeffrey Bodenhauser had asked a question saying, do you need to worry about skin effects in the metals? I think we partially addressed this, at least. Wasn't wondering if you had any other comments.
This is actually, this is quite interesting, and we do have a bit of a discussion in the paper if you are interested. So we were dealing with micron or so up to 10 micron size lithium particles, and so our RF skin depth is already bigger than that, so we don't need to worry about our RF penetration. The microwave penetration is very small. It's only it's, I think, nanometers at the surface for the correspondingly higher frequency. But it turns out that doesn't really matter, because your electrons are moving with a high kinetic energy, because they're near the Fermi level, they have a high kinetic energy. And so you can sort of picture them coming to the surface, interacting with microwaves, and then zipping off again into the bulk of the metal. And so here you have what's known as a spin depth rather than a skin depth, which is a combination of the kinetic energy of your electrons, which is dictated by your Fermi level, and the T2 of your electrons, so how long they retain that memory of interacting with the microwaves for, and therefore how far they get. And it turns out that that's also on the order of sort of tens of microns, so it's again bigger than our particles. So we actually get pretty uniform saturation of our lithium metal in this case.
And perhaps to add to this, the RF penetration doesn't seem to be so much of an issue. So we're sort of small enough to be able to excite all the lithium metal. We see that from the nutation curves for lithium metal, which look like normal nutation curves and are not smeared out towards the end.
Right, and skipping back a little bit, we're coming close to the end of time, but Marcel Levien asking, how far away from the metal phase can the lithium be to still get hyperpolarized by the irradiation of the metallic lithium?
Do you want to answer that one, Katerina?
That's something we're trying to find out. We'd like to know.
To be determined.
Again, it's very dependent on the mechanism. If it has to directly interact with the electrons, then that's one of the out of the six type dependence. That's have to be very close. But if it's if there's spin diffusion, then that's a very different story, and it depends on the density of the appropriate spins, and that's also not very well known, but it will be an interesting factor to investigate, because, as I say, this is a heterogeneous structure and it's not a uniform spin density.
All right. So we have 3 questions left. It is 6:30 at this time. If people want to stick around, we might have time to answer these last 3, but I'm not sure for recording sake if the full length will be able to be put on YouTube, but at the very least, I want to thank everyone for showing up and for supporting us. Make sure to check in next week as well for the talk by Quentin. At this point, I'll keep answering or asking questions as long as no one starts messaging me furiously telling me to stop. So going onwards, would it be possible / useful to use the oh yes, and to be certain, this will be uploaded on YouTube as well under the same account as the first video that we posted earlier today, or posted in the chat earlier. So would it be possible / useful to use the modulation schemes developed for proton decoupling to reduce microwave power needed?
Any idea, Katerina?
It would probably be useful.
So I guess this sort of requires hardware that's allows pulsing of the microwaves, which I know is sort of just coming online in some labs. So I think that'll be an interesting thing to look at in future when that's maybe more widely available. But everything we've been doing was continuous wave microwaves, and I'm not sure how we can really do any better than that without additional hardware.
All right. And next question for the Overhauser part. How would you expect the cross-relaxation rate and thus the hyperpolarization of the nuclear spins to differ from the 4 different alkali metals?
So I guess there's different effects. So your degree of cross-relaxation depends on your spectral density, and so that's going to be dependent. And also, so the spectral density is going to be dependent on the Fermi energy of the metal in particular, which changes the kinetic energy of your electrons. And then it also is going to depend on the strength of the interaction, and so on the density of states at the Fermi level, and the coefficient at the nucleus. And so, yeah, I'd expect that to be very different for 2s orbitals versus 3s orbitals, for instance. And also, it's going to be different for the different dispersions. So those are the factors that will dictate it, and I couldn't give you any idea of how that would change, for instance, from lithium to sodium.
And then the next question being from Sanjay, have you seen any 3-spin effects in the lithium-7 data?
I don't think so. Not anything that I would have spotted as a 3-spin effect. Katerina?
I think we can't really think about it like that, because in principle, we have a lot of electron spins, and every electron spin has 1 nuclear spin in the sample, in principle. So I think talking about 3 spin effects here as such is maybe not the right way to think about it.
Alrighty, and finishing up with our last question, if there are any more, feel free to comment them on the YouTube video when it gets posted. I'm sure that we will be happy to provide more answers and discuss further in that medium as well. But for our final question, in principle, would you be able to comment on what chemical compounds dominate the SEI, or which ones form first?
You want to take this one, Katerina?
Maybe you can bring up your SEI slide.
Yes, there we go.
So I think we're both not really battery and SEI experts to start with. So whatever we say, maybe don't take that as the absolute truth. But the general notion is that you start from like whatever is closer to the lithium metal is more inorganic, and then you get to the more organic compounds as you move further away from the surface of the lithium metal. I think that's what we could also see from the DNP experiments. Yeah, and
yeah.
Well, the kinds of compounds are sort of in that figure. I don't know if you want to add something like.
No, I think that covers it.
All right, then with that, I'd like to thank Dr. Hope and Dr. Marker for speaking with us today, and for giving a very wonderful talk, Michael, and also for answering our bevy of questions. And so, and also, of course, thank you for those who have stuck around to hear this part as well, and look forward to hearing from you all next week, and to get this to keep growing. Seems to be really wonderful. So thank you all, and pass it on to whoever wants to take control of the Zoom at this point.
Yeah, thanks everyone for coming.